It is essential for refrigeration professionals to know how various safety systems work, as these systems are designed to prevent mechanical damage and limit the dangers leaks create for both people and the environment. A gas detection system is the first line of defense for detecting and correcting refrigerant leaks. Halocarbons are odorless, so refrigerant detectors are critical for leak detection. Ammonia, on the other hand, has a highly pungent odor, so leaks are impossible to ignore. Although ammonia's self-alerting odor is a valuable safety feature, detection systems remain essential for establishing appropriate PPE requirements and for alerting personnel in unmanned areas if a leak occurs.
So there are many different types of refrigerant gas detectors available. Each have different pros and cons. One of the more common is the electrochemical sensor. The advantage of the electrochemical sensor is they have high sensitivity, so they can measure very low concentrations. A downside is they have a shorter lifespan, so the cell has to be replaced more often, and exposures to high concentration of gas could ruin the cell and it would have to be replaced as well. A second type of sensor is the solid state, sometimes called metal oxide. These ones have much longer lifespans, which is good. They do have a reduced sensitivity, so they're not quite as precise in their measuring. And a downside of these is that they are sensitive to other gases, so they're not as gas specific, and that could be a downside when trying to measure a specific gas. But they are, cost-wise, they're pretty cost-effective, which is an upside. So a third type is the infrared or IR sensor, and these are really good at measuring high concentrations, and they're employed for that purpose. Unfortunately, that does come at a cost, so they're quite expensive. A fourth type of gas detection that you should at least be familiar with, it's not as common, but is the Draeger tube. Now, these aren't like a fixed gas detector that you have on your wall, but this is used more by emergency responders to capture a known concentration. It's also used by industrial hygienists. And the Draeger tube is a glass tube that's designed to measure a specific gas. And what happens is you put it into a contraption and then break the tube, draw air through the glass, and it will measure a known concentration, which then can be sealed even for forensic purposes, like if you're really precisely wanting to capture how much of a certain gas was present. And finally, I'd be remiss if I didn't state you can use your nose, at least for some chemicals, some refrigerants like ammonia. Always want to be careful with that one, but for ammonia, it will be your first line of defense. Because it has such a pungent odor. Your nose or senses are not effective though on halocarbons, which generally are considered odorless.
Ammonia detection systems vary in their design and function. Some common features of an ammonia detection system include a low-level sensor in a machinery room capable of detecting between 0 and 250 ppm. This sensor is typically interlocked with horn and strobe alarms inside and outside the machinery room. This sensor is often interlocked to activate the machinery room ventilation system at 150 ppm. A high-level sensor in the machinery room, which should be interlocked with the machinery in the room to de-energize if the ammonia concentration approaches the lower flammability limit, or LFL. Often this sensor has a set point of 1 to 2%, which corresponds between 10,000 and 20,000 parts per million. Each room containing ammonia equipment, such as cold rooms with evaporators, should have a sensor that is interlocked to notify a monitored location in the event of a release. Some systems are configured with vent line sensors designed to notify facility personnel if a relief valve lifts.
There are many different types of refrigerant gas detections for personal use, and I want to just cover a few of those with you. The first here is that single gas detector. I'm holding here the ammonia detector that I often wear myself. This thing has a nice little clip. I can just clip it on my safety vest or whatever, and it records parts per million. And this is a passive device, so it doesn't have a pump or a vacuum or anything to sample the gas. So it just responds passively. I've got a bottle here of just household ammonia, 4%. And to show you how this thing works, I'll just kind of hold the cell over the opening there and watch the concentration increase. 6, 10. Once it hits the permissible exposure limit, you'll hear the alarm go off, just like that. So that's super helpful when you're working. Often you'll smell it first, but if not, this thing warns you that you need to get out of that space. Now, the second one that's pretty common you should be familiar with is the 4-gas sensor. And these are pretty widely used, especially for confined space entry. Now, the 4-gas sensor is measuring the concentration of 4 different gases. Now, these are not 4 different refrigerants. In fact, the standard 4-gas sensor or unit will be measuring oxygen, carbon monoxide, hydrogen sulfide, and LEL, which is measuring methane gas. But with hydrocarbons like methane and propane and butane, there's conversion, so it could really measure any of those gases. So it's possible when you order these though to switch out the hydrogen sulfide, which is the toxic concern, and replace it with a refrigerant, a cell of your choice, whatever refrigerant you have. So that's a good thing. But even if you just have a 4-gas sensor, it's helpful in measuring any unknown contaminant, because our normal air that we breathe is 20.9% oxygen. So if you see a drop in the oxygen level where it's 20.8 or 20.7, something has displaced it. So it can be helpful even to measure any unknown contaminant that's odorless, just by measuring the oxygen concentration. Now, the third one I'll talk about here, now this is specifically for halocarbon refrigerants, and I'm gonna turn this unit on, and maybe you can hear it, maybe you can't, but there's actually a little pump in here. So this has got a little sniffer on it so that you can use this to get it inside of a hard to reach area, put it into a coil, so that you can really detect the leak that way. Of course, the halocarbons are odorless, so you can't use your senses so well to detect a leak. So something like this can be really, really helpful. There are other devices that I don't have. A halide torch is one. I don't have it here to demonstrate, but it's a flame that's also used on halocarbon systems that changes colors based on the amount of refrigerant leak. It can be helpful in finding leaks. A spray bottle with soap in it to make little bubbles on a welded or soldered joint can be a useful tool, again, for odorless refrigerants. And finally, your own human senses. It may be that you can hear something that would be a more substantial leak, or in the case of ammonia, obviously, it's got a pungent odor, and that would probably be your first line of defense. So you'll smell it probably long before your sensor even goes off.
Machinery room ventilation is a cornerstone of safe design of a refrigeration machinery room. The ventilation system serves various purposes. If refrigerant leaks occur, whether ammonia, which is toxic, corrosive, and flammable at certain concentrations, or halocarbon refrigerants, which are asphyxiants, ventilation helps dilute and remove the gas from the room. Machinery rooms contain compressors, motors, and other equipment that generate significant heat. Continuous or intermittent ventilation helps maintain ambient temperatures within equipment design limits, preventing overheating and extending equipment life. Industry standards such as IIAR2 and ASHRAE 15 require machinery room ventilation. Compliance helps avoid fines, ensures worker safety, and satisfies insurance underwriting standards.
So let's talk about emergency ventilation for an ammonia refrigeration system. The current best practice, or RAGAGEB, for emergency airflow rate is 30 air changes per hour for an ammonia machinery room. And that comes from IIAR standard 2. So how would one go about calculating that? It's actually it's not too complicated. So let's say we have a machine room here, and I've drawn dimensions on it. This room is 40 feet long, it's 25 feet wide, and the average height of the room is 17 feet. And now the 30 air changes, what's the meaning of that? That means we need to take the volume of that room and we need to trade that out or exchange it 30 times every hour. So you can kind of visualize what that seems like. So let's first figure out what is the volume of our room. That's a pretty simple calculation. We're just going to multiply the length times the width times the height, 25 times 40 times 17, which equals 17,000 cubic feet. All right, so that's the volume of the room. We need to move that 30 times every hour. So our 30 air changes per hour is 30 times our volume, and divide that by hours, which makes it an airflow rate now. And this really arrives us at our answer, which is 510,000 cubic feet per hour. There's nothing incorrect about that, except that isn't a common unit that we use when specifying fans, okay? So we want to change this from cubic feet per hour to cubic feet per minute. So I'm taking my 510,000 cubic feet per hour and I'm just going to multiply it by the conversion factor, which is every 1 hour has 60 minutes. So 1 hour equals 60 minutes. That's like the equivalent of multiplying it by 1, all right? It doesn't do anything. Our hours will cross cancel here, and we'll be left with cubic feet per minute. So it turns out the fan that we need to supply 30 air changes per hour is 8,500 cubic feet per minute. or 8,500 CFM. That's a more common way to say cubic feet per minute. So as we look at this, we multiplied our volume times 30, and then we divided it by 60. So we can actually simplify this whole equation. It's kind of a little rule of thumb you can keep in your back pocket, which is 30 air changes per hour for any room equals 1/2 of the volume measured in CFM. As long as you use the volume in cubic feet, then multiplying that volume by 0.5 or dividing it by 2 will arrive you at the proper answer in CFM.
Local spot ventilation can be utilized by refrigeration technicians when maintenance activities may result in refrigerant release. Use of a portable fan can be effective to reduce the concentration to safe working levels. The king valve is the most noteworthy valve in a refrigeration system. Typically, an HPR will be configured with a single king valve that can be closed to stop the flow of ammonia from the vessel. This valve must be clearly labeled to aid first responders during an emergency. Some king valves must be manually operated, but others utilize a solenoid valve that can be activated remotely. A refrigeration e-stop is a safety control switch designed to immediately de-energize refrigeration equipment in the event of an emergency. System e-stops are typically installed outside the principal machinery room doors and control the power to all refrigeration equipment inside the machinery room. Other equipment, such as compressors, often have a local e-stop on the control panel, which will kill power to that machine in an emergency.
Pretty much every refrigeration system will have an e-stop, and it's important to understand when it's appropriate to use an e-stop and when it's not appropriate to use an e-stop. First of all, it's not an operational control, so don't use the e-stop just to start and stop your system. That's not appropriate. Even in an emergency, though, you want to apply principles of refrigeration before deciding if it's appropriate to activate an e-stop. So if we have a leak that's on the high side of the system, then it's great to use the e-stop, because hitting the e-stop will de-energize the compressors, which are the pressure-inducing components. So that will start to lower the pressure and reduce the release rate. So that is when an e-stop should be used. On the flip side, if a leak is on the low side of the system, let's say in an evaporator, it actually could be a bad thing to activate the e-stop, because the compressors are drawing vapor from the evaporators. So if we hit the e-stop, we stop the compressors. Now the leak from the evaporators is just stagnant and will continue to leak out and has no means of drawing that out of the pipes. So it's good to think about that ahead of time so that you know when you're going to use the e-stop and when you're not going to use the e-stop.
An emergency control box, or ECB, is a legacy safety system that is installed on older refrigeration systems. Sometimes called a dump box, an ECB provides a location to manually equalize pressure in a system or vent the refrigerant to the atmosphere. A typical emergency control box has 3 primary valves. Valve 1 is the high side discharge valve, Valve 2 is the low side discharge valve, and Valve 3 is the high to low pressure equalization valve.
One of the legacy safety systems on older ammonia refrigeration systems is the emergency control box. I've depicted that here. So what I've kind of drawn on the board here is just kind of like a very simplistic refrigeration system. It's not the basic cycle, because I've included more than just the compressor, condenser, expansion valve, and evaporator. I'm also showing a high pressure receiver, so the condenser drains into the receiver, and a suction accumulator that collects the wet suction and supplies dry vapor to the compressor. But the emergency control box is kind of an antiquated safety system. Before, there was like a ton of different controls available to monitor and operate a system. And the way it's set up is it would take a pipeline directly from the high side, typically the high pressure receiver, and go into this box, which is usually a metal box on the wall. And I've depicted that high side valve here, and it's in the closed position, which is appropriate. And then similarly on the low side, say from the suction accumulator or maybe a recirculator, take another pipeline, go into the box and connect it to a valve as well. Okay, and that valve, again, appropriately is in the normally closed position. The outlet of these valves are connected to one another and discharge straight to the atmosphere as I've depicted here, or it could be to a diffusion tank if a system was configured with one. And so you can now see pretty simply, if this valve were to be open, we're actually going to dump the refrigerant from our high pressure receiver to the atmosphere. And if we open this valve here, we're going to dump the refrigerant from our suction accumulator or the low side to the atmosphere. right? And there's a third valve inside the emergency control box, which is now connecting the two. And again, this valve is closed. And we call this the equalizing valve or the high to low connection valve. And then this is connecting our high side to our low side. And by opening that valve, if we were to put it in the open position, it would equalize pressure between the high and low sides of the system, which would prevent the system from operating properly. So now, why were these required, or how might these be used? In general, if you have an emergency control box, I would suggest you shouldn't be using it. Or at least if you are going to use it, it should be in the most extreme situations. But if you don't fully understand when and how it should be used, just don't use it, don't touch it. So obviously opening these two valves will vent your system to the atmosphere. There aren't a lot of good circumstances in which venting your system to the atmosphere would be a wise decision. However, I could just maybe point to a couple if I get pretty creative. If we have a catastrophic failure from our receiver or our suction accumulator, meaning it's such a situation that we're going to lose all the ammonia anyways, then maybe it would be a good idea to open these valves, because by opening them, venting them to the atmosphere, this is way up in the air. Ammonia, the weight of the ammonia is lighter than air, so it's going to tend to rise. It might be a safer situation than just allowing it to leak at ground level. Okay. Now, the equalization valve, that could be, there could be more use of that one. So if we have a leak somewhere from the high side of the system, it could be advantageous to open this valve to equalize pressure, because that will reduce the pressure on the high side as it flows into the low side. And that could help reduce the rate of release from the high side of the system. So I could see an advantage of using that. But in general, just explain this because they're still out there. You see them, and it's good to be familiar with how they're intended to operate.
An emergency pressure control system, or EPCS, is a pressure limiting safety system that replaced the emergency control box as a code-required safety system in the mid-2000s. The EPCS differs from the control box in many ways. The two most significant differences are: an EPCS is activated automatically, whereas an ECB can only be activated manually. An ECB includes a provision for manually discharging the refrigeration system to the atmosphere. An EPCS has no such provision. The EPCS functions as a relief device that activates during an overpressure event at a pressure higher than the pressure limiting device setting, but lower than the relief valve set pressure. When activated, it relieves the affected portion of the system by directing refrigerant through a solenoid valve to a lower pressure part of the system.
Okay, same diagram we've already looked at relative to the emergency control box, but now let's talk about the emergency pressure control systems. In the mid-2010s, the emergency pressure control system replaced the emergency control box in most major codes and standards. And this offers a superior safety system compared to the manually operated box. And really, it's kind of easy to understand what the EPCS does. It connects the high side to the low side through a solenoid valve, which is called a crossover valve. So, but because it's a solenoid and electronically controlled valve, this is now an automated safety system. So basically, the EPCS provides this crossover function that we had in the ECB, but it does it automated, and it has no provision for dumping the system to atmosphere. Basically, we don't want to do that in general. So how is this intended to work? Well, if you look at our layers of protection when it comes to overpressure protection, our first line of defense is typically the compressor high discharge pressure cutouts. The compressor is designed with their own safety devices that will shut it off if the pressure becomes too high. But let's say that fails. The next line of defense on older systems was often a relief valve, let's say installed on the compressor or a high pressure receiver that was designed to protect the equipment from rupture. The EPCS provides an intermediate safeguard, which is once the pressure's exceeded the discharge pressure cutout, but below the relief valve setting, this will activate and relieve pressure from the high side back to the low side. So in that sense, this is like an overpressure protection device. This is not a relief valve, it is a solenoid valve assembly, but its kind of intended function is to be similar to an overpressure protection device. And the set point requirement is that it be at 90% Could be less than that, but 90% of the relief valve setting. So typical situation, if we have a 250 PSI relief valve, 90% of that would be 225 PSI, which would be the set point at which the solenoid would open, relieving pressure. So maybe the compressor is designed to cut out at 200, this activates at 225, then the relief valve is our final fail-safe at 250.
Refrigeration systems must be configured with signs, labels, and markers to identify components and warn personnel of hazards. Pipe markers must indicate the direction of flow and refrigerant name. Ammonia pipe labels must additionally include the physical state, relative pressure, and service abbreviation. All major equipment, such as compressors, condensers, evaporators, and vessels, should be affixed with a permanent component marker that displays the equipment name and ID number. Machinery room doors must be clearly labeled. For ammonia machinery rooms, IIAR suggests that all entrances to a machinery room include the following information: refrigeration machinery room, authorized personnel only, caution ammonia R717, caution eye and ear protection required, NFPA 704, ammonia fire diamond, blue 3, red 3, yellow 0. IIAR also requires that system signage be installed that contains at least the following information: instructions for shutting down the system in an emergency, the contact information for whom to contact in an emergency, the maximum intended inventory of ammonia in the system, the type of refrigerant compressor oil, and the low and high side design pressures.